In this video, we will be talking about solving exponential and logarithmic equations. Before we do that, we need to recall a couple of things, mainly the properties of logarithms and exponential equations that we've gone over so far in this chapter. So the first thing we need to know is the product property. So log base a of u times v is equal to log base a of u plus the log base a of v. Then we need to know the quotient property. So log base a of u divided by v is equal to log base a of u minus log base a of v. Then the power property. So log base a of u to the power of n is equal to n times log base a of u. Then we need to know the more general properties of logarithms. So log base a of 1 is equal to 0. Log base a of a is equal to 1. Log base a of a to the power of x is equal to x, and a to the power of log base a of x is also equal to x. Then the one-to-one property. So if log base a of x is equal to log base a of y, then x is equal to y. And we need to know that for both logarithms and exponentials. This lesson will mostly boil down to using all three of these and these two down here. So in this lesson, we will need to be able to move from both left to right in each of these equations, but also from right to left. So we need to be able to expand and condense, and we need to be able to use the one-to-one property in both directions. So there are two basic strategies for solving exponential or logarithmic equations. The first is just using the one-to-one properties. So expanding or condensing a logarithm or exponential so that we can set the exponents equal to each other or what's inside the log. The next is using the inverse properties. And this is basically canceling out logs or the bases of exponents. So if you think about it really simply, you can undo multiplication using division. You can undo addition using subtraction. The same is true for logarithms and exponentials. You undo logarithms with exponentials, and you undo exponentials with logarithms. So the two strategies really boil down to rewriting the original equation in a form that allows the use of the one-to-one property, or canceling out bases or logs using the inverse property. So a couple of examples on how to do this. So in each of these examples, we will be solving for x. So in the first one, e to the negative x squared is equal to e to the negative 3x minus 4. And we can solve this in one of two ways. We can use the one-to-one property, and just because we have the same base here, we can just cross it out and set negative x squared equal to negative 3x minus 4. If we add over the x squared, we get 0 is equal to x squared minus 3x minus 4, and that is a quadratic, which we can solve in a couple of different ways. We can graph it, find the x-intercepts, we can factor it, or we can use the quadratic formula. Because we can factor it pretty easily, you can set 0 equal to x minus 4 times x plus 1, and then set each of these factors equal to 0. So x will equal 4, or x will equal negative 1. The other way to do this is to use the inverse property. And in order to do that, we want to take the log base e in order to get rid of the e's on the inside. So if we do that, we take the natural log on both sides. And because the natural log is log base e, the natural log and the e's will cancel. And then it's the same problem as we just did in red. So we would set negative x squared equal to negative 3x minus 4. And again, x would equal 4, or x would equal negative 1. Each of these are okay to do. It's really just whatever you feel more comfortable with. The next problem says 3 times 2 to the power of x is equal to 42. Now, if you ever are multiplying something outside of the base, the first thing you need to do is to get rid of that. So we need to divide both sides by 3. When we do that, we are left with 2 to the power of x is equal to 14. Now we need to cancel out 2 to the power of x. So we need to get rid of this base of 2. Again, in order to do that, we have to use the inverse property. So we need to take a log base 2 of 2 to the x. And because we did that on the left-hand side, we have to do it on the right-hand side. This log base 2 cancels out the base of 2, so we're just left with x. So x will equal log base 2 of 14. The next one says e to the power of x plus 5 is equal to 60. Again, we got to get rid of this plus 5 on the outside. So e to the power of x will equal 55. And then we need to cancel out this e. So again, we have to take the natural log on both sides, or log base e. When we do that, we have the natural log of e to the power of x is equal to the natural log of 55. The log base e and this e on the inside, they cancel, so we're just left with x. So x will equal the natural log of 55. For the next one, 2 times 3 to the power of 2t minus 5 minus 4 is equal to 11. So in this case, we have to follow the order of operations, so we have to add 4 to both sides. So we're left with 2 times 3 to the power of 2t minus 5 is equal to 15. Then you need to divide by 2. So you're left with 3 to the power of 2t minus 5 is equal to 15 over 2. And now we're in the same position. So we need to get rid of this base of 3. In order to do that, you need to take the log base 3 of both sides. So when we do that, we have the log base 3 of 3 to the 2t minus 5 equals log base 3 of 15 halves. The log base 3 and the 3 on the inside cancel, so we're left with 2t minus 5 is equal log base 3 of 15 over 2. Then we just need to treat this as an algebraic problem, where log base 3 of 15 over 2 is just some number. So then we add 5 to both sides, so 2t will equal log base 3 of 15 over 2 plus 5, and then we need to divide by 2. So t will equal all of this divided by 2. A couple more examples that are more logarithmic. The first, the natural log of x is equal to 3. In order to cancel out this natural log of x, we need to take the natural log as an exponent of e. So what that looks like is e to the power of ln of x is equal to e to the power of 3. So this is the inverse property, it's just working the opposite of way of what we were just doing. So this e to the power of the natural log, that cancels, so we're just left with x, and we're left with e cubed. And in this first step, we had to take e cubed because we took e to the power of ln of x. So what we do to one side, we have to do to the other. In this next one, log base 3 of 5x minus 1 is equal to log base 3 of x plus 7. We have the same base log, so we can just use the one-to-one property. So 5x minus 1 is equal to x plus 7. If we subtract x from both sides, we get 4x minus 1 is equal to 7. So 4x will equal to 8, and x will equal to 2. In the next one, log base 6 of 3x plus 14 minus log base 6 of 5 is equal to log base 6 of 2x. Now, going back to the properties that we had before, we have the difference of two logs with the same base, so we can combine those a little bit. When we do that, we get log base 6, and we're subtracting, so we're going to have a quotient. So it'll be 3x plus 14 over 5, and that'll still equal log base 6 of 2x. Then we can use the one-to-one property, so 3x plus 14 over 5 will equal 2x, multiplied by 5 on both sides. So 3x plus 14 will equal to 10x. Subtract 3x, and then divide by 7. The next one, 2 times log base 5 of 3x is equal to 4. This 2 on the outside has to go in one way or another, so you could put it as an exponent, but it's probably just a little bit easier to divide first. So if we divide both sides by 2, we get log base 5 of 3x is equal to 2. Now we need to cancel out this log base 5 so we can get x by itself. In order to do that, we take each of these two sides as an exponent of 5. So what that looks like is 5 to the power of log base 5 of 3x. And because we did that on the left-hand side, we had to do it on the right-hand side. So this will be 5 squared. This 5 to the power of log 5, they cancel, and we're just left with 3x. So 3x is equal to 25. And x will be 25 over 3. So now that we are a little bit more comfortable using these properties and solving logarithmic or exponential functions, we can go back to the first thing that we did in this chapter, or one of the first things, which is continuous growth of money. So say you deposited $500 into an account that pays 6.75% interest compounded continuously. How long will it take to double your money? So a couple of things that we need to pull out. Our initial value is $500, so that's P. And we're doubling our money, so our A will equal 1,000. Our rate is 0.0675, and we're compounding continuously, so we're using A is equal to principal times e to the power of our rate times time. So when we plug all that in, we get 1,000 is equal to 500 e, the natural base, times our rate times time. So when we're solving for this, we have to get e to the power of whatever we're trying to find by itself. So we need to divide by 500 first. So we get 2 is equal to e to the power of 0.0675t. And then in order to get rid of the e so that we can get t by itself, we have to take the natural log on both sides. So when we do that, we get the natural log of 2 is equal to the natural log of e to the power of 0.0675t. The left-hand side will stay the same. On the right-hand side, this natural log and the base of e will cancel, so we're just left with 0.0675t. And then we can just divide by this rate. And when we do that, we will get the natural log of 2 divided by 0.0675 will equal t. And we can plug this into our calculator and just get a number. So instead of going to our calculators and graphing it, finding the intersect and fixing the windows and all of that, we can just solve using the inverse properties and everything we just learned. And when we plug the natural log of 2 divided by 0.0675 into a calculator, we get 10.27 years. Again, possibly a little bit quicker than using your calculator, but this is just a different way of doing it. So before we finish, I would like to do a couple of examples just to reinforce some of these things. Um, these are all found in the exercise section of 3.4, and I'll just start with number 13. So 4 to the power of x is equal to 16. We have solved this before in class by using the one-to-one property. You can still do that, so we can rewrite 4 as 2 squared to the power of x is equal to 2 to the 4th. Then we can clean up the exponents, so 2 to the 2x is equal to 2 to the 4th. We can cross out these bases, so 2x is equal to 4 and x is equal to 2. Number 17, the natural log of x minus the natural log of 2 is equal to 0. Because this is a difference of two logs with the same base, we can combine them. So we can rewrite the natural log of x minus the natural log of 2 as the natural log of x divided by 2, and that will still equal 0. In order to solve for x, we need to get rid of the natural log. So we need to take everything as an exponent of e. So if we rewrite that, it'll be e to the power of ln of x divided by 2 is equal to e to the power of 0. This e and the natural log will cancel, so we will just be left with x over 2, and e to the power of 0 will be 1. And when we multiply both sides by 2, x will just be 2. On number 20, e to the power of x is equal to 4. We want to get rid of this e, so we need to take the natural log of both sides. And again, the natural log is log base e. When we do this, the natural log and the e cancel, and we're just left with x. And we need to take the natural log of 4 as well. So x will equal the natural log of 4. Number 21, the natural log of x is equal to negative 1. In order to get rid of the natural log, we take everything as an exponent of e. So if we write that, we get e to the power of ln of x is equal to e to the power of negative 1. This e and the natural log cancel, so x will equal 1 over e. Number 23, log base 4 of x is equal to 3. In order to get rid of the log base 4, we need to take everything as an exponent of 4. So when we do that, we get 4 to the power of log 4 of x is equal to 4 cubed. This 4 and the log base 4 cancel, so you're just left with x. So x will be 4 cubed, which is 64. Number 33, 4 times 3 to the power of x is equal to 20. The first thing we have to do is get rid of the 4 on the outside, so we divide 4 on both sides. So we're left with 3 to the power of x is equal to 5. Then in order to get rid of the base of 3, we need to take the log base of 3 on both sides. So that these two bases cancel each other out. So we're left with x is equal to log base 3 of 5. A couple more examples. So number 29 says e to the power of x is equal to e to the power of x squared minus 2. Because both bases are the same, they can cancel, and we can use the one-to-one property. So x will equal x squared minus 2. So 0 will equal x squared minus x minus 2, which again is a quadratic that we can solve in a number of different ways. But this is easy enough to factor. So 0 will equal x minus 2 times x plus 1. So x will equal 2 and negative 1. Number 37, e to the power of x minus 9 is equal to 19. The first thing we have to do is add over this 9. because it has nothing to do with the base of e. So when we do that, we get e to the power of x is equal to 28. And then in order to cancel out the base of e, we have to take the natural log of both sides. And when we do that, we get the natural log of e to the power of x is equal to the natural log of 28. The natural log and the base of e cancel, so you're just left with x. So x will equal the natural log of 28. Number 40, 6 to the power of 5x is equal to 3,000. In order to cancel out the base of 6, we have to take the log base 6 of both sides. So when we do that, we have the log base 6 of 6 to the power of 5x is equal to log base 6 of 3,000. This log base 6 and the base of 6 cancel, so 5x will equal log base 6 of 3,000. And then divide by 5 on both sides. So x will equal log base 6 of 3,000 divided by 5. Number 43, 3 to the power of x minus 1 is equal to 27. In order to cancel out the base of 3, we have to take the log base 3 of both sides. So when we do that, we get log base 3 of x minus 1 is equal to the log base 3 of 27. Now, on the right hand side, we can actually simplify that a little bit more. So 3 cubed is 27, so this right hand side will simplify to just 3. And this should be 3 to the power of x minus 1, so that these cancel. So then we'll be left with x minus 1 is equal to 3. If we add 1 to both sides, x will equal 4. And then number 57, 6 times 2 to the power of 3x minus 1, and then minus 7 is equal to 9. So first we have to solve this. We have to do a little bit of algebra first. So if we add 7 to both sides, we get 6 times 2 to the power of 3x minus 1 is equal to 16. Then we have to divide by 6. So 2 to the power of 3x minus 1 is equal to 16 over 6. In order to cancel out the base of 2, we have to take the log base 2 of both sides. So we get log base 2 of 2 to the power of 3x minus 1 is equal to log base 2 of 16 over 6. When we do this, the log base 2 and the base of 2 cancel. So we'll be left with 3x minus 1 is equal to log base 2 of 16 over 6. And again, the rest is just algebra. So if we add 1 to both sides, 3x will equal log base 2 of 16 over 6 plus 1. And then we have to divide 3 on both sides. And when we do that, we get x is equal to log base 2 of 16 divided by 6 plus 1, and then divide all that by 3. So hopefully these examples cleared up at least a couple of things, but for now, a couple of key items to keep in mind. There are 2 basic strategies for solving exponential or logarithmic equations. The first is using the one-to-one property, and the second is using the inverse properties. If we know how to use both of those, these are fairly easy to do with practice. So our goal is to use the properties in order to solve logarithms and exponentials. If you keep it simple, just remember that logarithms undo exponents and exponentials undo logarithms. And as of right now, that is how we will be solving exponentials or logarithms.